Welcome to Business Calculus, otherwise known as Elementary Applied Calculus. This is the review section for those of you who need a review of your algebra principles. So just going to quickly go through some of the ideas. Remember, this is a recording, so at any time you can stop it if you need to write down a formula and then start it back up again when you're ready. The review chapter does kind of skip around a little bit, so sorry, the topics don't flow all that well. It's just the way the book set them up. There are more items in the review chapter, and I have posted the notes in D2L. So if you want some other examples and things, those are in the notes in D2L that go along with this slideshow. So the first thing I want to talk about is this is the compound interest formula. Okay, so this is the compound interest formula. Okay, so P stands for the principal amount, meaning the beginning amount. So if you were depositing money in a savings account, that would be the amount we deposited. R is your rate. N is the number of compounding periods. And you'll notice that N is up here. And then T is time in years. Okay, so let's go back to N though, compounding periods. So if something compounds monthly, then there are 12 compounding periods. If it compounds annually, then there is one compounding period. If it compounds quarterly, then there would be 4 compounding periods. So let's go to the next slide to see how we can use this. Okay, so let's suppose that we put $1,000 into an account. 8% is our interest rate. Now remember, we can't put it in as an 8. We need to convert that, so it needs to be 0.08. That would be the decimal equivalent, compounded quarterly, so that means 4 compounding periods and 3 years. So that's going to look like this. 1,000, there's your principal. 1 plus R goes on the top, so that's the 0.08, divided by the number of compounding periods. And remember, this exponent is going to be 4, the number of compounding periods, times 3, the number of years. So this is going to be 1,000 times 1 point. Okay, this is 1.02 to the 12th power. Let's see what that is. 1,000. Okay, which gives us $1,268.24. Okay, so that would be the total in the account at the end of 3 years. Okay, next we're going to talk a little bit about functions. We're going to be working with functions. This is kind of a cumbersome definition. The easier definition for a function is for every x value that you put in, that's your domain, those are your x's, there is only one y. I'll write that out. For every x, there is only one y. So let's look at some functions. All right, so these are examples of stocks. So on a specific date, you have exactly one output, one value at the end of the day for that particular stock. And you'll notice each date only has one value. Okay, so we're saying every time we put a number in, we only get one answer out. We're not getting two answers out. Let's look at more examples though. Okay, this would be something where this is also a function because every time we put in a number, when we put in 3, we get out 9. When we put in 4, we get out 16. When we put in 5, when we input 5, we get out 25. When we input -5, we get out 25. It doesn't matter that -5 went to 25 and +5 also went to 25. There's no rule that says they can't go to the same output. The rule says for every number I input, for every X value, I only get one answer out. So here, when we inputted 5, we only got one answer out, 25. When we inputted -5, we only got one answer out, 25. Okay, we're going to skip through these. Okay, so is this a function? So let's think about this. If we have a table of values, X and Y, let's say -1. Let's just start putting some numbers in. If I plug -1 in, the answer is 1. If I plug 0 in, 0 squared is 0. If I plug +1 in, +1 squared is 1. If I plug 2 in, 2 squared is 4. So anytime I put a value in, anytime I input an X value, I only get one value out. So the answer to that is yes. Again, it doesn't matter that those two X values, 1 and -1, both had the same output. Okay? The graph of a function. We get all crazy about graphing. Remember, graphing is just plotting dots. You're just making a dot at the place where you have the X and Y that go with it. So the X is the number that you're plugging in, the Y is the number that came out, and you're just plotting that point. So if we go back to the last example, if we have -1 and 1, when we were to graph that, so we would have -1 is here, and +1 would be there. We'd put a dot here at -1, 1. Okay, 0, 0 would be a dot here. 1, 1 would be a dot here. We're just putting dots at those ordered pairs, and then we connect them to make the graph. And here's another example of a parabola that they have graphed. Okay, if you have a function, so if something is a function, if you draw a vertical line, now remember, this, ooh, that's a really ugly vertical line. It's supposed to be a little more straight up and down. That's a vertical line. When I draw a vertical line on a graph, I should not be able to cross the graph of my function more than once. If I do, it is not a function. That's what the vertical line test says. Okay, so let's look at these. Are they functions? If I draw a vertical line, does it cross my graph more than once? So it does not, so this is a function. What about B? If I go here and I draw a vertical line, does that cross that graph more than once? Yes. Okay. That means that for this one X value, there are two different Y values. So that's why this vertical line test tells us if something's a function. So this is not a function. I think you get the idea there. All right. Something we're going to use in this class, or you at least need to be able to read, is called interval notation. So when I'm trying to say that I go from one number to another, if I use parentheses, like this first example, that means that A is less than X and B is bigger than X, but we don't include whatever number A and B are. A and B are not included. So we use this parenthesis to indicate that they are not included. We can't equal those numbers. If we want to equal those numbers, we have to use the square brackets. That means that A is included and B is included in the set. And then, of course, you can do variations on that where A is included, but B is not included. A is not included, B is included. There is a special rule when we go from a number to infinity. Since we can't ever actually reach infinity, there's always one more. Infinity always has an open bracket. Okay, and again, the same thing with negative infinity, it's always an open bracket. Remember, negative infinity to positive infinity, this one is all real numbers. That's how we denote all real numbers. So let's practice that a little bit. So in interval notation, well, I'm going to look right here at this less than equal. So I have -2 to start. And this says it can equal it. So I'm going to make the square bracket, comma, and then over here, it goes up to 5. It says it can equal it. So again, square bracket. On the next one, I have an equals here. So square bracket, -2. This one didn't have an equals though. So when we get to the 5, I've got to use a parenthesis. Okay, on this one, we have -2. No equals with that less than symbol, so that's a parenthesis. Goes to 5, and we do have an equals, so that side square. And then this last one, neither one of them has an equals, so they're both going to be parenthesis, -2 to 5, parenthesis. All right. So one thing that we have to be really good at finding, this is going to be very important in calculus class, is finding the domain. So when we are thinking about domain, remember, is x values. What x values are we allowed to use? Like, is there any number that we're not allowed to put in? When I say that, I mean, in order to not be allowed to use a number, it's got to break some math law. Okay, and there are only 2 times that that's ever going to happen. I cannot have a denominator that is equal to 0. I can't have a 0 in the bottom of a fraction. Okay, so this one is a fraction, so we have a possible problem. So the way you work it when you have a fraction, take the denominator. So in this case, our denominator was 2x minus 5. And let's set that equal to 0, not equal to 0 in this case, and let's solve. So we'll add 5 to both sides, so 2x not equal 5, which means x cannot equal 5 divided by 2, 5/2. Okay, that is the only number that is excluded from the domain. So our domain would be negative infinity to 5/2. Remember, I can't include 5/2. We're not allowed to use it. Union 5/2. We're starting again on the other side of 5/2 and going to infinity. We are excluding this one number because it causes the denominator to be equal to 0. If you plug 5/2 in here for x, this whole denominator would turn into a 0, and that is not allowed. This is the second time that you will have a domain problem. We cannot have a negative under a radical. And I should say negative under an even radical. You can have a negative under a cube root. You cannot have a negative under a square root. Okay, so you can take the cube root of negative 64 equals negative 4. The square root of negative 64 is not a real number. And in this class, we're only using real numbers. So in order to solve for this, what we're going to do is take the 4 plus 3x, and I want that to stay greater than or equal to 0. It could be 0, because I can take the square root of 0, but I can't let it get smaller than 0. So as long as I keep it bigger than 0, I'm fine. So let's subtract 4 from each side. So we get 3x has to be greater than or equal to negative 4, which means x has to be greater than or equal to negative 4 divided by 3. That is your domain, every number bigger than negative 4/3. So this in interval notation would be negative 4/3, comma, infinity, and then an open bracket. That's just supposed to be an infinity there. It's not supposed to be crossed through. I want to look at a couple others. Before we go here, let's scroll down. So let's suppose we had this. Y equals 2x plus 1. The domain of that is all real numbers. That's not a fraction. It's not under a radical. So I want you to learn where these rules of domain, which state always start with the idea that it is all real numbers. And you better have a darn good reason if you tell me that you have a domain that is not all real numbers. I better see a fraction or an even radical. A linear function has a domain of all real numbers. Okay, these are the only two times you are going to have a domain that is not all real numbers, unless we artificially restrict the domain ourselves, but we'll get to that later. Okay, so let's look at these two. Now, again, it's a fraction, so it could have a domain problem. Take that denominator, set it equal to 0, and solve. So x cannot equal 8. That's the only number it can't equal. In interval notation, negative infinity to 8, union 8 to infinity. Okay, on B, we have 2x minus 8 has to be greater than or equal to 0. 2x has to be greater than or equal to 8, which means x has to be greater than or equal to 4. So this one would go, I can equal 4 this time, 4 to infinity. Okay, y equals 4. This is a special line, so I just wanted to point it out quickly. Y equals 4 is a line. You'll notice it right here. It is this blue line. It is a horizontal line. So y equals, anytime you have a y equals, it will give you a horizontal line. If you have the equation x equals some number, in this case it's x equals negative 3, this gives you a vertical line. So anytime you have x equals some number, it will give you a vertical line. Now, x equals some number is not a function because it will not pass the vertical line test because it is a vertical line. Okay, those are two special lines because we're going to talk a little bit about lines now. Okay, linear function. Okay, remember we want to write them in this form. Y equals mx plus b. M is your slope, and B is your y-intercept. M is the slope, B is the y-intercept. Okay, if you have a positive slope, the lines will look like these. They start down here and go in this direction. Since we read from left to right, it looks like we're going uphill. These are negative slopes. They start high and get low. So those are examples of negative slopes. Okay, we've already looked at this, but this particular form, this y equals mx plus b, is called the slope-intercept equation of a line because you have your slope here and your y-intercept is right there. There's another equation that we have. We're going to use both of these to find the equation of lines when we are given points. So this one, we have y minus y1 equals m times x minus x1. This is called the point slope equation of a line. So that's when you are given a point and the slope. You can use this to find the equation of the line. So let's look at some examples. We want to find the equation of a line with a slope of 3 containing the point -1, -5. So, oops, a little too far. Okay, so this will be, sorry, this will be your slope intercept side. So on this side, we're going to say -5 equals, our slope was 3 times -1 plus b. Okay, so we have -5 equals -3 plus b. We're going to add 3 to both sides. We want to get b by itself. So adding 3, we get -2 equals b. Now, on slope-intercept, we have to put that back into the equation. Remember, we're looking for y equals mx plus b. So we know y equals, we know the slope is 3, and we know that b is -2. We can do that same thing with that point slope formula. So that would be y minus -5 equals 3 times x minus -1. Okay, minus negative means plus. So we have y plus 5 equals, I'm going to go ahead and distribute over here, 3x plus 3. Okay, we want to subtract 5 from both sides so that y is by itself. So we have 3x minus 2. So we got to the exact same place regardless of which method we use. So what do you do if you aren't given the slope? Okay, so the answer to that is we have to be given 2 points in that situation, and we would subtract the y values, subtract the x values. This is your rise, your change in y, over your run, your change in x to calculate the slope. Now remember, doesn't matter which order you do your y's in, but whatever y you use first on top, you must use that x first on the bottom. So let's look at another example. This time we were not given the slope. So we're going to have to calculate the slope. So let's do that first. We have m equals, okay, so we need our y values up on top. So I'm going to say 9. Since I use 9, -4 has to go right below it. Minus 6. That means -2 has to go that. So that's minus -2. It's going to be a plus 2. So 9 minus 6 is 3. -4 plus 2 is going to be -2. So my slope is -3/2. Okay, now I want to use this to find the equation of the line. We're going to go one step further. They only asked for the slope, but let's go ahead and get the equation. So if we use slope-intercept, and it doesn't matter, you can pick either of these points. These numbers look a little smaller, so I think I'll go with those. So using slope-intercept, that would be 6 equals -3 halves times -2 plus b. So 6 equals, and I have -3 times -2, which is +6. +6 divided by 2 is 3, plus b. We're going to subtract 3 from both sides, so 3 equals b. So our final equation would be y equals -3 halves x plus 3. If you do the same thing using that point slope, we would have y minus 6 equals -3 halves x minus -2, so that's going to be plus 2. So we have y minus 6 equals -3 halves x, and then we have -3 times 2, which is 6 divided by 2, so we're going to have -3. Then we're going to add 3 to both sides because we've got this 6 over here, so add 3 to both sides, so you get -3 halves x, add 6 to both sides. When I add 6 to both sides, I'm going to get -3 halves x plus 3. So it doesn't matter which way we do it, the answer will be the same. Okay, here is a business example. So we have a clothing firm. We're going to talk about total costs, revenue, and profit. And we're going to talk about how each of those is calculated. So costs are made up of two types of costs, your fixed costs and your variable costs. Revenue, remember, don't confuse revenue and profit. They are not the same thing. Revenue is all the money you bring in. Okay, revenue is every dollar you bring in. So we are not worried about cost when we're talking about revenue. Revenue can be a huge number, but if our costs are bigger, then our profit won't be good. Okay, but we do not use costs to calculate revenue. Revenue is simply price we sold it at times quantity sold. Price times quantity, that's it. We're not going to take out the cost. To get profit, we're going to take our revenue and subtract the costs. Okay, so here we have $20 per suit variable costs. We have fixed costs of $10,000 a year, and we are going to sell these for $80 a suit. Okay, so our total cost is our variable costs plus our fixed costs. So for this one, it is 20 times X, because remember, your variable costs vary with the number of the item we make. So how many of them we make. Fixed costs doesn't matter how many of them we make. If we don't make any, our landlord is not gonna tell us you don't have to pay rent this month. You're still gonna have to pay that rent. Revenue is price times quantity. So in this case, the price was $80 and the quantity is X. So R of X is 80X, C of X is 20X plus 10,000. Profit is R of X minus C of X. Now, be careful when you're doing this. You have to make sure that you are distributing this negative if your cost function has more than one term. Okay, so we have 80x minus parentheses 20x plus 10,000. Okay, this negative gets distributed to both. So this is going to be 80x minus 20x minus 10,000, which makes our total profit 60x minus 10,000. That is our profit function. And then we can choose any x, any number of suits that we made to figure out what our total profit would be. Okay, break-even point is that point where revenue and costs are the same. Break-even means we didn't make any money, but we didn't lose any money. Our profit was zero. Okay, so in order to find a break-even, we're going to set revenue equal to cost. Okay, so here, if we set revenue, let's go to the next slide, revenue equal to cost, we have 80x equals 20x plus 10,000. Subtract 20x from both sides, so we get 60x equals 10,000. And then we're going to divide both sides by 60. So we get 166 and 2/3. Okay, now let's try to remember we were making suits. And I don't know anyone who's ever made 2/3 of a suit. Don't think we could sell 2/3 of a suit. So we're going to round that up. We don't want to round that down because then we'd be a loss. I'd rather have a tiny profit than a loss. So let's round that up to 167 suits being our break-even point, because we do need to sell whole numbers of suits. Okay, some other kinds of functions. There's a quadratic function, ax squared plus bx plus c. Okay, we're going to be factoring those, so you need to remember how to factor. Quadratics make parabolas. That's a parabola. That's a parabola. They are cup-shaped. They open up like this if this leading coefficient is greater than 0. And they open down like a frowny face if your leading coefficient is less than a 0. If, in other words, negative. If we want to find the vertex, we're going to take x equals negative b over 2a, and that will give us the x coordinate of the vertex, and then you plug that back into your function to find the y value. So let's find the vertex of this one. Negative b, well, b is already negative 2, so negative b is going to be, negative b is going to be a positive 2, negative negative 2, over 2 times a, which is 1, so that is going to give us 1. So our x value, this is x equals, is 1. Let's go ahead and plug 1 in here into this function and see what our y value is. So we have 1 squared minus 2 times 1 minus 3. So we have 1 minus 2 minus 3. Well, 1 minus 2, that's going to be negative 1. Minus 3 more would be a negative 4. So our vertex is going to be at 1, negative 4. Okay, plug your x value back into your original function to get the y value. Okay, and there's a graph of that function. It found some points that plot your vertex. Vertex is important because it's this spot down at the bottom. Pick a few points on each side and you can get that nice shape. Okay, quadratic formula. Before we'll go into this. Okay, so here's your quadratic formula. And you're going to want to jot this down. Negative b plus or minus the square root of b squared minus 4ac, and all of that is over 2a. Okay, this is what you use when you cannot factor. You can get the solutions this way, but I do want to talk for a minute about factoring. So let's look at some problems that we can factor. And let's see, that's not what I wanted to do. Insert blank page, that's what I want to do. So let's look at a couple of problems. We have x squared minus 2x minus 3. Okay, so we want to find two numbers. They will multiply to give us a -3. That means one has to be negative and one has to be positive, but they add to give us a -2. So that means they're going to be -3 and 1. Those are the factors of -3 that will add to a -2. So our factors are x minus 3, x plus 1. You should remember this factoring from college algebra. This is a skill that you need in order to even start calculus. I'll give you one more. X squared minus 5x minus 24. Okay, so I want factors of -24. So again, one's negative, one's positive, but they add to a -5. In this case, the factors of -24, and you can list them out, would be -24 and 1, -12 and 2, -8 and 3, -6 and 4. And look for which pair adds to be a -5. So it is the -8 and 3, which means our factors are x minus 8 and x plus 3. Okay, when you cannot factor, for example, I happen to know that this one is not going to factor. Now, before you start, do remember this 2 has to get moved to the other side. So it should look like this before we start. The whole thing needs to be set equal to 0. A is 3, B is -4, and C is -2. So now that we have all that, we're going to put that all into the quadratic formula and get our answer. Remember, this plus or minus here means we are going to end up getting two answers. It is, let's change that, -4 would be a +4. So this is going to be 4 plus whatever this number is divided by 6, and then 4 minus whatever this number is divided by 6. So let's see what we get. Oops. Sorry about that. I guess they didn't show us the answer. So 1 second, and I will calculate that for us. So we have 4 plus 6.32 divided by 6. So one answer is 1.72, and the other answer is 4 minus 6.32 divided by 6. So the other answer was -0.39. Those are the two answers that you get using the quadratic formula. All right, a few other things you need to know these properties of exponents. So when I have two like bases with different exponents and I am multiplying the bases, we add the exponents together. So for example, x squared times x to the 5th is x to the 7th, if I can get my pen to write. If it doesn't want to write. Okay, so that should say x to the 7th. There we go. Okay, if we are dividing, so if we had a to the 4th over a squared, we're going to subtract, and our answer is a squared. This is power to a power, so if I have x cubed squared, then I would have x to the 6th. And then this is a really important one, this last one. You have to be able to move negative exponents around and know that x to the -2 is the same as 1 over x squared. The other one that you need to know that I don't think is on this page, so we're going to add it, is the square root of x. You need to be able to rewrite that as a rational exponent. Square root of x is x to the 1/2. This is the power, so this was being raised to the power of 1. And remember, when there's nothing written here, that's an assumed square root, so it's a 2, and that is the root. Okay, those are the exponent properties that you need to know. So if we were going to rewrite these, this one is x. The power here is 1. Nothing's written, so it's a 1. And then we've got a root of 4, so that's 1/4. Okay, here we have r. The power is 2. The root is 3. X, power is 10. The root is 2, which simplifies down to x to the 5th. That's why they had to tell us that. And then finally, this one is 1/b to the 5/3, which equals, I don't want it in a fraction anymore, so that is b to the negative 5/3. Okay, you need to get comfortable with being able to rewrite those rational exponents. Oops. Okay, those are just some more examples using numbers. So if you have 8 to the 5/3, it means the cube root of 8 raised to the 5th power. So cube root of 8 is 2. 2 to the 5th power is 32. If we add 81 to the 3/4. Now you can take 81 and raise it to the 3rd power first, but that's more difficult. 81, if I take the 4th root of 81, that happens to be 3. And if I cube 3, I get 27. Okay, exponential functions. Remember, the important thing about an exponential function is that the variable is in the exponent. Graph of an exponential function. Okay, demand function. We're going to talk really quickly about supply and demand functions. So demand functions, as the price gets higher, the quantity demanded gets lower. Consumers' demand is inversely proportional to price. So as price gets higher, demand gets lower. Okay, supply function. As the price gets higher, we are willing to sell more. So that varies directly. Higher price, higher quantity. Okay, we want to find something called the equilibrium. And that is going to be, let's get to the next slide. Oh, I don't think they gave us the graph of that. All right. That is going to be where your supply and demand functions cross. So let's just suppose that was our demand function. That would be your equilibrium, where they cross each other. Algebraically, if we want to find that, so if you want to, you can graph it, and where they intersect would be your answer. If you want to find it algebraically, though, we're going to take the demand function, which in this case is 50 minus 1/4 x, and set it equal to supply. So let's go ahead and solve that. 50 minus 1/4 x equals x minus 25. Well, let's go ahead and add 25 to get that off of this side. Add 25. Okay, so we're going to have 75 minus 1/4 x equals x. Now I need to add this 1/4 x and add 1/4 x. And when I do that, okay, remember, this has a coefficient of 1. And in a fraction form, 4/4, common denominator, is the same as 1. So now I have 4/4 plus 1/4. So I have 75 equals 5/4 x. In order to get this fraction off of here, let's multiply both sides by 4. So I'm going to multiply this by 4. That gets rid of the 4. Multiply that by 4. So 75 times 4 is 300 equals 5x. And then divide both sides by 5. So x equals 60. So our equilibrium is at a price of $60. And we could plug that back into either one of them because this is equilibrium to find our quantity. So $60, 60 minus 25, and it would be for 35 units. I forgot what they are. Are they bags of coffee? Ultrafine coffee makers. So 35 coffee makers at $60 a coffee maker. Okay, we already did that. And that, oh, I guess it was in hundreds of coffee makers, so 3,500 coffee makers. All right, so that is it for your review section. If you have any troubles with any of those, I encourage you to go look on YouTube. Also look at the review section notes. Those will help you as well. Come to class with any questions on any of the videos that you watched on your assigned day.